Alright, this video is going to help you with the electrochemical cells lab. Before I get too far into what you're going to be doing in this video, I want to go a little bit into the chemistry behind it. This is one of the topics we weren't able to get to as much as I would have liked. So I wanted you to at least do a lab to introduce you to it, if nothing else. Oxidation-reduction reactions were one of the types of reactions we talked about back at the beginning of the year. And you see at the top of this, it says from reactions with oxygens, with your sugars, your fats, your proteins, or just fuels in general, to metal corrosion. There's a lot of reactions that involve oxidation reduction. The citric acid cycle and the electron transport chain are a few that come to mind. Sorry for those of you in AP Bio. But fuel cells, there are so many reactions that involve redox reactions. That I just wanted you to get an idea of how powerful those could be in terms of the voltages that you measured. Okay? So the first thing we're going to just review is that electrochemistry is basically a study between how chemical reactions can produce energy that can be harnessed in the form of electrical current. Okay, and that these types of reactions, redox reactions, occur when electrons are transferred from the reducing agent to the oxidizing agent. Electrons have to be lost for electrons to be gained. Okay, and that in order to balance a redox reaction, you actually have to write the half reactions for both components. And for the ones that we're going to do, they're going to be pretty simple. You don't necessarily have to do this. But there are more complex ones that would require you to balance elements such as hydrogen and oxygen using water and whether the solution is acidic or basic. But the other important characteristic is that you have to balance the charge. You have to account for the fact that the number of electrons lost has to equal the number of electrons being gained. So this was not one of the reactions you did, but if you had a combination of lithium and iron, you could balance this equation by writing half reactions for each component. So in this particular one, lithium formed lithium plus ions, and so in order for that to happen, it had to lose an electron, while iron went from being 3 plus to iron, so it had to gain 3 electrons. Well, the only way one can lose an electron and the other one can gain 3 is for them both to undergo a change of 3. So you would have had to multiply the lithium half reaction by 3 to account for that electron change. And now the electrons lost do equal the electrons gained. And the balanced equation would be 3 lithiums and an iron 3 ion make 3 lithium ions and an iron metal. In this particular redox reaction, lithium lost electrons, so it was being oxidized, and it would have been at the black terminal in your lab. It would have been the anode. Well, iron was gaining the electrons, and since electrons have to be lost for them to be gained, it would have been at the red terminal. That would have been where your iron electrode was, because it was at the cathode. It was undergoing reduction. I think this may have been one of the reactions you chose to do in the second part of part 1, between aluminum and magnesium. No, actually, I don't think y'all had aluminum, so I don't think you got to do this one either. Sorry. We would split this one in half again between aluminum ions and aluminum, and magnesium ions. This time we see that aluminum is gaining 3 electrons, while magnesium is losing 2 electrons. So we need to find a common factor with that electrons that are being transferred, which would be 6. So the aluminum half reaction would be doubled, while the magnesium half reaction would be tripled. So we would have had 6 electrons being lost, while 6 electrons would have been gained, leaving us with 2 aluminums and 3 magnesium metals make 2 aluminum metals and 3 magnesium ions. So because aluminum gained electrons, it would have been at the red terminal. It would have been undergoing reduction, so it was at the cathode. Magnesium was losing electrons, so it would have been at the black terminal. It would have been undergoing oxidation. Okay. So electrochemical reactions occur where that until you have that electrical current that's connecting them, you're not going to see the electron transfer occur. You have to be able to have the two pieces together. We needed the salt bridge in our connecting the two electrodes, the two wells, so that the charge buildup, because one would become positively charged and one would become negatively charged, doesn't happen. That salt bridge allowed ions to move between them to balance out the ions being lost. Okay? So oxidation always occurred at the anode and reduction occurs at the cathode. And for your purposes, the black terminal was your anode and the red terminal was your cathode. Okay? So here's kind of a drawing. These would be the adjacent wells. This would be the salt bridge that was kind of overlaying. This is actually a little bit different. It's called a porous disk, but it's working the same way. We see the electrons moving from anode to cathode. Okay. Oh, sorry. We have zinc here. It is losing electrons, so it's going from zinc metal to zinc ions. While copper is gaining electrons, so it's being replaced on this plate. So the mass of this electrode would be increasing, while the mass of this electrode would be decreasing. And the amount of electrons that are being transferred in the form of potential energy, the voltage is a measure of the potential energy change per unit charge. And that has to do with our electrons. Okay? So I didn't ask you to sketch a cell, but this was one between copper and silver, and I just thought that might kind of help you see what was happening in your lab. You do not have to do this for any part of your lab. So if you don't want to watch this, you can scoot right on through it. Silver gained an electron, copper lost 2 electrons. So when I balance that equation out, I would need silver to gain 2 electrons, which is why I see 2 in front of both silvers in the final reaction. Copper was losing electrons, so it's acting as my anode, while silver was gaining electrons, so it's acting as my cathode. The copper metal was in the copper solution. The silver metal was in the silver solution. Electrons moved from the anode to the cathode, and I can use the half voltages of both of these cells, the reduction potential of copper and the reduction potential of silver, to calculate what the voltage change should have been. We'll do that a little bit later. This part here is just showing how ions move. Because you made more positive ions, negative ions from the salt bridge move that way. While here, because you lost positive ions, cations move in to the cathode to balance out that decrease in positive charge. So the cell potential, the E cell, what you measured, basically was just the pull as the electrons moved from anode to cathode. And it's, again, the change in your potential energy per unit of charge, which depended in part on how many electrons are being transferred. And so voltage, which you've often heard referred to, 1 volt, is basically a joule per coulomb. A coulomb is representing your charge. Now, I gave you at the end of your lab a sheet that looked like this. And these were reduction potentials. And you have these for each of your metals. I know you needed one for silver. You needed one for copper, you needed one for zinc, you needed one for magnesium, there's the one for zinc, you needed one for iron, I think that's it, I think you had 6, magnesium, zinc, iron, 3 copper, silver, maybe it was just 5. I thought it was 6. I'll double check when we go back to the lab to make sure. Copper, you need one for lead. You did need 6. Let me go see if I can find one for lead. If not, I will look one up for you guys. Yeah, I don't see lead on this chart, so I need to get you one for lead, and I will get that right now so I don't forget it. Lead reduction potential. So, let's see if I can shrink this. So I'll make sure I tell you this in class, but lead's reduction potential is negative 0.13. Okay? There it's on the whole page, so that should make it a little easier to see. So we want to make sure you write this one down, that lead's reduction potential is negative 0.13 volts when 2 electrons are gained to make it PB. Alright, so that's your sixth one that you'll need for this lab. Okay, these are based on the voltages that would be generated when they were combined with hydrogen. Hydrogen's defaulted to 0. I'm not real concerned about this bottom part, but I just thought that might help you some with the questions. Basically, the greater that voltage difference is for the reduction half reaction, the more willing that substance is to be reduced, while the more negative it is, the less willing it is to be reduced. So that's why you saw magnesium down the bottom. It's a more reactive metal. It's not as interested in going back to being pure magnesium. It would much be more willing to be oxidized, and so it would be more willing to lose its 2 electrons. So to calculate the voltage potential, you basically just add the 2 half reaction voltages together. Because they were all written as reductions, the one that was at the black terminal will have to be flipped because it will no longer be written in that direction. It'll be written as an oxidation half reaction, so its voltage would go from being positive to negative or negative to positive. One nice thing about voltages is that the number of electrons being transferred has no effect on the amount of energy that is being generated, since it's already per unit of charge. So we don't have to worry about accounting for any changes in the coefficients when we balance those half reactions. I told you to measure positive voltages because that's when you have a reaction occurring spontaneously. So in this particular one with copper and silver, I would go and look at my chart and find the copper half reaction and the silver half reaction. And so when I split that reaction in half, copper makes copper 2+ ions, silver plus gains an electron to make silver. The reduction half reaction would be written as 0.337 volts, but because I had to reverse it, it's now written as negative 0.337. The silver reduction reaction gets written just as it was on the chart, and I would add those together to get the cell voltage for the reaction. Okay, notice that even though I doubled the silver to make it a balanced equation, the voltage did not change. It's still 0.462. Okay, now I know I have a little bit more to show you. I think there's a couple more slides. But if we go back to the lab, so you all collected data, and I asked you in part 1 to record measured voltages. And I left you a space to record the net ionic equation, the theoretical voltage, the anode, and the cathode. You should have been able to go ahead and record this part as well, leaving just the net ionic equation and the theoretical voltage alone. So I said here in number 1, I wanted you to write balanced net ionic equations and use the electrode potentials from the table of voltage potentials at the end of your lab. Again, I put it at the end of your lab. I don't think it's on this particular sheet, but it was the one I just showed you from the other page. I know that I double checked though, and this is on your lab. Okay. So for the first reaction we had between zinc and copper. So zinc has a voltage potential of negative 0.763 volts. Copper has a cell potential of 0.337 volts. So zinc was at our anode, so this reaction would have flipped, or in terms of its voltage potential, to 0.763. Copper's would have been left alone, 0.337, and we would have added those together, and I think you would have gotten a voltage of around 1.1. When these two reactions are combined, because they both resulted in a transfer of 2 electrons, we would have zinc plus Cu2 plus makes Zn2 plus plus Cu. Alright, because the reactions would have been flipped. So with that in mind, my reaction would have looked something like this. Because I need to reverse, I don't want two reduction reactions, I can only have one. And because they have the same number of electrons being transferred, I would just switch the zinc 2 plus and zinc, and I would show that the number of electrons being transferred was equal and the number of zincs and copper were equal. So your net ionic equations are just going to be like this. You cannot show this first one. Okay, you got to do another one. And I do want you to show me how you came up with that one. The theoretical voltage would be the copper reduction, okay, minus or plus the zinc oxidation voltage, which again would be flipped. Alright, so you should get positive voltages for these, and you're going to do this for the other ones, but you only have to show me one example of the net ionics, and you only have to show me one example of the electrode potential calculation for this voltage, and then the rest you can just do. Okay? And so then in number 2, you're going to compare the theoretical to the actual. I'm not making you do percent errors. I asked you to tell me which one was the most similar and which one had the biggest difference. So you're going to look at these and see which ones are closer together and which ones are way far apart. And that's all I'm after you to look at, just to see how does your data match up with what's on that chart. Number 3 and number 5, number 3 and number 6, I'm going to have you write balanced equations between the zinc and the copper and zinc and the silver. So that's what you're going to use to fill in table 2 and 3, just like you did in table 1. And you've already labeled your anode and cathode. I am going to ask you to do a little bit more with part 2. I want you to calculate what the voltage should have been based on the diluted concentration of your copper using this crazy thing called the Nernst Equation, and that's what I'm going to go back to the PowerPoint right now to talk about. So the Nernst equation basically accounts for the fact that you don't always have concentrations of 1 molar. You guys aren't going to have to worry so much about this one. You get to use the one at 25 degrees to make your life a little bit simpler. You've already done a calculation for the zinc versus copper, and that's going to be your standard voltage potential. And you already know that 2 electrons got transferred. And so what we want to know is how that concentration changed. How would that affect the new cell potential? So as you diluted your copper concentration, since copper was reduced, the copper ions were a reactant. And according to our Q versus K, if the reactant concentration decreased and we were at equilibrium, we would need to shift towards that reactant concentration to reestablish it, which means our voltage probably should have decreased from that standard amount. And so this is an example of a calculation you would be able to do to finish up part 2 of your lab. It's asking here to calculate K. I'm actually going to hold off on this one for a second and then move on to the next part. There we go. So it says in this one, if silver had been reduced to 0.6, what would the new cell potential be, and would it be spontaneous? So this was the reaction back between copper and silver that I showed you when we drew the cell out. And so if the silver ion concentration went down, similar to what happened in your lab, your copper concentration went down, what would the new cell potential be? So Q is basically your K expression. You don't get to include the pure metals. You only get to include the ion concentrations. So it would be the copper concentration over the silver concentration squared due to the coefficient. Copper didn't change. It was still at 1 molar. Those are your standard concentrations. And if you remember Everything in your lab, other than the ones that you diluted, were at a concentration of 1 molar. The silver now is at 0.6. All right, and so if the silver went down to 0.6, the copper had to go up to 1.2. Now, I'm telling you in this one it was reduced. We made ours separately, so in your lab, the copper concentration went down, but the zinc concentration stayed at 1. Regardless, you can use that to calculate your Q value. In this particular case is 3.3. So when I go through and do my calculations, this N is your moles of electrons. That's your standard voltage, and this is a constant. So what you will need to substitute in for yours is the standard cell voltage for zinc and copper. You will need to put 2 in for your volts, 2 in for your moles of electrons transferred, and then you'll put in your value of Q, which will be the 1 molar over, I believe it's 0.001 molar, which is what you made of the copper ions. And we do see that the voltage did get reduced, which would make sense since the silver ion concentration went down. We would need to shift back to balance out the silver ion concentration that was lost. Okay, so if we go back to your lab, it says here again, you're going to use the Nernst equation to calculate what the expected voltage should be. So if we go back to part 2 of your lab, you made a 0.0010 molar copper 2 nitrate solution, and then you added 1 molar zinc to the other well. So your zinc concentration was 1, your copper concentration is 0.001, and you're going to use both of those to calculate what the new cell potential would be with that decrease in copper ions in your solution mixture. Okay? Once you have calculated what it should be, you're going to compare it to what you actually got by calculating percent error, and we're going to see how close they were. So it says, how did the change in copper ions affect the cell potential? Did it increase it? Did it decrease it? Does this make sense based on Le Chatelier's principle, and why or why not? Alright, so I had to do a redo on part 3. My brain's getting a little fried from making all these videos. So in part 3, we are trying to figure out what the KSP is of silver chloride. You can get that from a book, but we want to see how close we can come to that true value for the KSP of silver chloride. We are going to assume, because silver chloride breaks into silver and chlorine ions, that we know that the concentration of chlorine is going to be roughly 1 molar because we added a large excess of it. We have to figure out what the concentration of the silver ions are in order to calculate the KSP. And we're going to use the Nernst equation and the voltage that we recorded to help determine what that silver concentration was, similar to what we did in part 2. So in part 2, you measure the cell voltage for an unknown silver chloride, in an unknown silver solution along with zinc. And so you can calculate the standard voltage between zinc and silver using your table of reduction potentials that is at the end of your lab. So you would take your zinc cell potential and you would take the silver cell potential. I believe you're going to need to flip the zinc one, and you would get what the standard voltage potential would be for the two, around 1.5. So if we go back to the Nernst equation that we used in part 2, if we know what the potential was based on what we measured, and we know what the standard potential was, and we know how many electrons transferred, we can calculate what Q was. We also know what the half reaction is between zinc and silver. So we know what Q is equal to, what the ions are in the numerator and what ions are in the denominator. The zinc ions remained at 1 molar. So if we know what the Q value is, and we know what the zinc ion concentration is, we should be able to calculate the silver ion concentration. If you need more help with that, please feel free to ask. I know that was a fair amount, but trust me, that was better than the first time through. Alright, so once you have calculated the silver ion concentration, which is what you're asked to do in number 6, you're going to calculate the KSP for silver chloride. KSP is just the silver concentration times the chlorine concentration. So your answer to number 6 and the information provided in number 7 should make that one fairly straightforward. You do want to make sure you record that over there in the chart. And then I ask you to calculate the percent error for your KSP of silver chloride. I will tell you that the KSP of silver chloride, you should be able to get the theoretical value by either Googling. I know it's in your textbook in chapter 18, but I do want you to find that value. And then you're going to calculate the percent error to see how close your experimental silver chloride KSP value is, the one that was based on your data, is to the true value of silver chloride. And then I ask you, what does a negative value for a standard potential indicate? So what have you gotten from all this? Why was it I made you measure positive voltages or positive potential values? And if it's negative, what does that tell you is actually happening? Okay? If you have any more questions, please don't hesitate to